Hello everyone! In this video, we will begin to examine stellar evolution. In particular, we will focus on the following understandings: the HR diagram, stellar evolution on HR diagrams, red giants, white dwarfs, neutron stars, and black holes, Chandrasekhar and Oppenheimer-Volkoff limits, as well as sketching and interpreting HR diagrams, sketching and interpreting evolutionary paths of stars on an HR diagram, describing the evolution of stars off the main sequence, and describing the role of mass in stellar evolution. So far, up to this point, we have focused on the main sequence, but many stars exist off of the main sequence. Why is that? And the answer is due to what we call stellar evolution, which is the process by which stars change over time as time goes on. You can visualize stellar evolution on the HR diagram. So on this HR diagram, we see that a solar mass star, a sun-sized star, will evolve off the main sequence and undergo a series of changes over time. And as it undergoes those changes, its properties change, and so we'll explain those changes in this series of videos. And the important principle to remember is that the changing properties of those stars over time is almost exclusively a function of the initial mass. So the initial mass of the star will control what happens to it, when, and how. At the beginning, it's important to note that stars form from what are called protostars. Protostar just meaning before star. Although you will not have to discuss this evolution in general, the general idea is that stars form from dense enough clouds of dust and gas. Those clouds of dust and gas are either in the interstellar medium, so just generally the stuff between the stars, that's what interstellar medium means, or from formal nebulae. So those are larger clouds of gas and dust, or perhaps more condensed clouds of gas and dust that form from a number of different reasons. And those clouds condense under gravitational pressure. They reach the main sequence, that is, those protostars condensing from the clouds of gas and dust reach the main sequence in an amount of time that is related to the eventual mass of the star. Lower mass stars take longer to condense. The more mass you have, the more gravitational pressure, and therefore the quicker. So a 15 solar mass star here is only going to take on the order of about 1,000 years to reach the main sequence. Oh, I'm sorry. That's going to be 10 to the 5th years or so, whereas a 1 solar mass star here will take somewhere on the order of 1 million to 10 million years to reach the main sequence. On the main sequence, we've already talked about this, but on the main sequence, the stars are in hydrostatic equilibrium. That is the equilibrium that occurs between the radiation pressure due to hydrogen fusion in the core of the star and the gravitational pressure as that mass condenses inwards. But the methods of heat transfer in the star do depend on how big the star is. And although we won't get into this in detail, you can see that a very small star mainly transfers heat via convection from the core. A medium-sized star around the size of the sun will have sort of an inner radiation transfer-dominated region and then an outer convective layer, whereas really big stars, bigger than about 4 solar masses, will have an inner region dominated by convection and an outer region dominated by radiation. This matters in the evolution of the stars every once in a while. The most important thing to see on this particular slide, though, as we've already talked about sort of the main sequence in detail, is the dependence of the main sequence lifetime on the initial mass of the star. So if we take a look at this here, we'll find that very, very big stars don't live a little bit shorter lives than smaller stars. They undergo their entire main sequence lifetime in a factor of 10,000 to 100,000 times faster than sort of more normal, ordinary solar mass size stars. Notice this unit is in 10 to the 6th years, and so a 25 solar mass star is only on the main sequence for about 4 million years. This is in contrast to a 1 solar mass star, where the main sequence lifetime will be something closer to 12 billion years, or a factor of 12,000 times. This is because they're much bigger, they are much brighter, they are much hotter, and therefore much more luminous, and as a result, they burn through their nuclear fuel way faster. All right, so what we're going to do over the next series of videos is talk about what happens to a star after the main sequence and how it depends on the original mass. Although the story is very complicated, it is simplified for the IB into two general categories. Low mass, that is stars between about 0.6 to 8 solar masses. Notice we're not talking about the very tiniest stars, the ones that are about half the mass of the sun to lower than that, about 0.2 solar masses. So generally low mass, including 1 solar mass and up to stars that are 8 times the mass of the sun, and high mass, greater than 8 solar masses here. And what you can see is that the outcome, what happens to those stars, depends on their initial mass. To read this left chart here, we would say that if the initial mass is about 1 solar mass, then as we'll talk about, the sun will become a red giant. It will give off a planetary nebula, and we'll discuss that. And then eventually its core will become a white dwarf, and the size of the white dwarf can be read on this bottom scale here. And so what we're going to do is we're going to sort of group all of these things together and discuss their evolution. And then we'll group all of these things together and discuss their evolution. The remnant, that is the final result, does depend on how big the initial star was, and we'll talk about that as well. And the general 3 categories of remnants we'll discuss are white dwarfs, neutron stars, and black holes.